So today we're going to be looking at the lesson 5.4 notes on graphing and comparing ratios. Example 1 says comparing ratios. So we're going to have, the problem says you mix 8 tablespoons of hot sauce and 3 cups of salsa in a green bowl. And they're going to mix 12 tablespoons of hot sauce and 4 cups of salsa in an orange bowl. And we want to know which one is hotter. Okay, so the first thing we did was to record that in a ratio table so that we can get organized. Ratio table is always a nice way to organize your information. So we've got the number of tablespoons of hot sauce to salsa, which is the first part of the problem, 3 cups of salsa, 8 tablespoons of hot sauce. And then in the orange bowl, there are 12 tablespoons of hot sauce and 4 cups of salsa. And then we have to have some way of comparing this information. So you start out like this. And it's like, well, how do I decide which is hotter? 8 to 3 or 12 to 4? I need some sort of common denominator. Right? So I look at 3 and I look at 4. And I'm like, in order to compare those, just like when you're comparing fractions, you need a common denominator. A common denominator for 3 and 4 is 12. So if I multiply 3 times 4 to get 12, then I'm going to multiply 8 times 4 to get 32. Whatever I do to the denominator or the bottom, I do the same thing to the top. Notice that we're multiplying, not adding. When you're working with a ratio table, multiplication always works better than adding. All right? And then in the second problem, I multiply 4 times 3 to get 12. So I do the same thing to 12 times 3 to get 36. And now I'm comparing this last column where I have the same number of cups of salsa. So when we have the same amount of salsa, which one has more hot sauce? Oh, this one has more hot sauce. Okay, so for 12 cups of salsa, orange bowl has more hot sauce. So it is hotter. Okay, and then, whoops, you see that? All right. And so then you have a you try that you should do. Same problem setup, but now you're going to mix 10 tablespoons of hot sauce and 3 cups of salsa. And now we want to know which one is the mildest. Okay, so you're going to make a ratio table with 10 to 3, and then you're going to find some common denominator so that you can compare all 3 bowls. All right. Okay, let's look at the next page. Okay, example 2 is comparing unit ratios. This is one of the most powerful things, one of the most useful things that you can learn how to do. All right, this is a super useful everyday skill, is comparing unit rates. A unit means 1. Okay, so we're finding the rate for 1. When you compare unit rates, you can find which one is more or which one is less for an individual item. All right. So here we've got 2 things of dog food on the shelf. Sometimes it's different size packages. In this case, you've got a 30-pound bag compared with a 20-pound bag. Sometimes it's at different stores and the size of the package is different, and so you're comparing the 2 different things. We want to find out the cost per pound. Per means to divide. We're going to put the cost per pound. Okay, this is per. That's dividing. All right? That fraction line is the same thing as division. If you see the word per in a problem, that's what that means. All right? So to set this problem up, they've again used a ratio table. They start out with the cost per pound. The first, the 20-pound bags are $17.20 for 20 pounds. And the 30-pound bag is $25.20 for 30 pounds. Okay, so just organize your information first so that you can compare the two things. Okay, now where you're going is you want to find the cost for 1. That's the cost for 1 pound. All right. In order to get there, you're going to divide by 20. 20 divided by 20 is 1. And then you can do $17.20 divided by 20. And you get out your calculator. And you do $17.20. And you divide by 20 equals 0.86. That's 86 cents. Right? So that 20-pound bag costs 86 cents per pound. All right? Then you do the same thing with a 30-pound bag. I want to get this down to 1 also so that I can compare how much it is per pound. I'm going to divide both sides by 30. And if you use your calculator and you do $25.20, and I divide that by 30 pounds, that's the cost per pound, it tells me that that is 0.84. That's 84 cents. Problem asks me, which is the better buy? The cheaper one is the better buy. 30 pounds is cheaper. I guess let's call that the 30-pound bag. The 30 pounds is not cheaper than 20 pounds, but the 30-pound bag is cheaper per pound. Okay? You try, it's a similar problem with packs of paper towels. So you've got a 30 pack for $48.30 or a 32 pack for $49.60. You need to do the math, right? You need to set up a problem and do the math with either do some long division or get out your calculator. It's not asking you to guess or to do some kind of reasoning. It's asking you to do the math, right? You need to find the cost per roll. All right, so let's substitute in. Then you put in the $48.30 per 30 rolls. All right, and then you do this math. And then you compare them and get the answer. All right, there will be a problem like this as one of your essential standards. And I'll expect you to do math, not to just guess. All right. The last problem is another one that you're going to see as an essential standard or essential assignment. And that is graphing values from ratio tables. I love graphing. I love how it connects to algebra. I love how you can see things, right? So the problem says we have a hot air balloon that rises 9 meters every 3 seconds. So there's the balloon, 9 meters for 3. And we have a blimp that rises 7 meters for 2 seconds. Have you seen the Goodyear blimp that flies around? Well, I guess it used to fly around. All right, so we're comparing the rate for the hot air balloon versus the rate for the blimp. All right, so here's the balloon. You have done ratio tables like this in the last chapter when we did some graphing. This is going to be your X value. This is going to be your Y value when we start graphing. We'll talk about that a little bit more in a minute. Okay, and just organizing that information. So right from the problem, you see balloon 9 meters every 3 seconds. So in 3 seconds, rises 9 meters. And then it goes up. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. All right, and then 9 times 2 is 18. 9 times 3 is 27. 9 times 4 is 36. All right, you have to do the same thing to both sides. And in this case, it's going up evenly. It's going up the same amount each time. That should always be the case. Okay, same thing with the blimp. It starts out after 2 seconds. It has gone up 7 meters. So we can go here. 2 times 2 is 4. And 2 times 3 is 6. And 2 times 4 is 8. So doing the same thing here. 2 times 2 is 14. Times 3 makes 27. And 7 times 4 is 28. Okay? Whatever you do to one side, you have to do the same thing to the other side so that they stay proportional, so that the rate stays the same. All right? You can't do one thing to one side and one thing to the other side, because then the rate is not constant. It's changing. It's not proportional. Okay, and then it asks you to graph that information. So we're going to push it up here. Let's see if I can get it. I'm going to have to kind of go back and forth. Okay, so we're going to graph the ordered pairs, time and height from the tables in part A. All right, so on a graph, this is your x-axis. The x-axis is the independent variable. Remember that from chapter 7? That's independent. And the y-axis is the dependent. All right, and if I'm thinking about time and height, the height that the balloon or the blimp goes depends on, I wrote it back, yeah, this depends on how much time has passed. All right, so time is your independent variable, and that is in seconds. And your dependent variable is the height, and that's in meters. Okay, and just for handiness, that's always the case, almost always. If time is one of your choices, it will be on the x-axis, because you really can't change time, right? Time is always independent, and how fast things happen depends on the time. All right, so let's graph. Let's see, we need to choose a scale. When I'm looking at my time numbers, I see that it goes up to 12 is the biggest number I have. And so I am going to number on my x-axis by ones. All right, remember that this is 0, so you have to start counting here at 1. And I'm going to number the lines, not the spaces, because when I put a dot, I want to put a dot on a, like on a lattice point, right? I'm going to put it on the line. I'm not going to put it off in a space somewhere unless it's a fraction, which I don't think it will be this time, because all those were whole numbers. 9, 10, 11, 12. Okay, and then I need to choose a scale. Maybe we'll put 0 there just for good measure. All right, then we need to choose a scale for our y-axis. So looking down here, your y-axis goes up to 36. I think that we need to count by, we're going to count by 4s. All right, we count by 4s. That'll graph nicely. So starting with 4, 8, 12, 16, 20, 4, 8, 32, 36. You could have chosen a different number. 2, I slide it back down there. 2 works nicely with these numbers. 1, but it would not fit all on your graph. You could have chosen something bigger like 10, but then it's really hard to graph a number, if the scale is too big, then it's hard to squish it in there, all right? All right, so let's just graph our points. I'm going to go on the balloon, I'm going to go over 3 and up 9. Okay, so I'm going to do balloon in purple. Okay, I'm going to go over 3 and up to, let's see, here is 8, there's about 9. Okay, and then let's see, 6 18s. I'm going to go over to 6. There's 4, 5, 6, and there's 16. Halfway between 16 and 20 is 18, and over 9 and up 27. Here's 28, so 27 is there, and over 12 and up 36. You should notice that it is a straight line, right? It's a straight line because the balloon is rising at a steady rate. It's going up 9 meters every 3 seconds, going up steadily. Okay, and it starts here at 0 because when no time has passed, the balloon hasn't gone up at all. All right. Alrighty, and let's switch ink colors. Hopefully the pink will be different enough. Can we see that? Oh yeah, good. I love pink. All right, so this is the blimp. And I'm going to go back to that information at the top, and I'm going to go over 2 seconds and up 7 meters. So over 2 and up 7. And let's see, this one, probably about there. All right, and let's see, over 4 and up 14. 14 is halfway between 12 and 16. Okay, over 6 and up 21, not there. And over 8 and up 28, right there. All right, and again, they should make nice straight lines. Okay, going to be real exact when you graph, and it should end up going through 0, 0 also. Okay, so when you are graphing, actually let's go back to the ratio table. We're going to answer the question 2 ways. All right, so let's slide down. Okay, first it asks you which rises faster. So just like when we were looking at the salsa and we had to compare which one had more hot sauce for a common denominator, this time you're looking for a common number somewhere. When I look down here, I don't see any common numbers in the height, but when I come over to the time, I see that they both have a 6. There and right here. So at 6 seconds, the balloon has gone up 18 meters and the blimp has gone up 21 meters. So the blimp is higher. It has gone up faster. Okay, so the blimp is higher. Okay, let's look at that on the graph. When I come to the graph, here is 6 seconds. At 6 seconds, I can see that the blimp is higher than the balloon. Okay, the answer on the graph is the same as the answer that I had in my ratio table. And I can also see that the blimp line is above the balloon line, even though they started here at the same place. They both started at 0. The blimp line is above. The slope is steeper. It's going up faster. Right? So when it asks you, what can you conclude? We can conclude that the blimp let's see, the blimp slope is steeper. Does that make sense? This is if you're going up a hill, that's a steeper hill. Okay, so the blimp slope is steeper because it is rising faster. Okay, you have one you try to do with that. Now it says if the blimp rises 6 meters every 2 seconds, how does that affect your conclusion? So you need to make another ratio table and put in 6 meters for 2 seconds and then graph that and see where it falls. Does that make the blimp go slower than the balloon, or is it still going to be faster than the balloon? Okay.